Okay, good day. This is AP Calculus. I am Mr. McCully, and this is the presentation for section 7.1, the area between two curves. Let's get right after it because this one could be kind of a long one. Okay, so our learning goals. Find the area of the region between two curves using integration, and then find the area between two intersecting curves using integration, and then describing integration as an accumulation process. All right, that's what we're going to do. So first thing, the area of a region between two curves, a definition. If f and g are continuous functions on some given interval a to b, and the function f of x is greater than g of x for all the values of x inside that uh, interval a to b, then the area of the region bounded by f and g between the vertical lines x equals a and x equals b is given by that function. The area is equal to the definite integral from a to b of f of x minus g of x dx. So what does that mean? All right. So just a real quick visual interpretation. So the first thing that says we have two functions, and so we'll just do our regular xy axis. So we had our x and our y axis. And so first off, we want to talk about values between a closed interval from a to b. And so we have some function here. We're going to call that function f of x. And then we have a second function right here. And we want it to not be exactly the same. So we're going to call this function right here g of x. And for every value of x inside this interval from a to b, f of x is bigger than g of x. So what we can do is we can draw two fairly simple lines. Let's make it kind of small right here. And we can find the area between those two curves as a highlighted region, this region right here. And that region is just going to be let's get to the right pen here. It'll be the integral from a to b of f of x minus g of x dx. That is that area right there, A. Okay, so what happens when the curves do intersect? Well, that's a little bit more challenging, but the same concept basically applies. So let's say, again, we have, well, let's do it the same way we did it. So let's go A to B. There is our closed interval on the x-axis, and there's our y. And so let's say in this case, g of x does the, or f of x does this. Let's say this is my f of x function. And then let's say g of x does this. All right. Well, the area between these two curves on this closed interval has to be, again, let's make our vertical lines here. Vertical lines is going to be this region right here. And then we need this part in addition to it. So the area between those two curves is that. And so that poses a problem because for part of the function, f of x is above, and for part of the function, g of x is above. So basically what we have to do is we have to find this point of intersection and call it C. And then what we have to do is we have to basically split this up into two integrals. The integral from a to c when f of x is above g of x, and the integral from c to b where g of x is above f of x. And so we'll just write that. So the area here, the yellow area, is going to be that first integral from a to c where f of x is above g of x. So it's just going to be f of x minus g of x dx. And then to that, we're going to add the integral from c to B, that's not a very good C there, Macaulay. Let's get with it, try and do a better job. All right, from C to B of g of x minus f of x dx. All right. And so if you're asked to find the area between two curves, especially on an extended response question, you really need to graph them and see if they intersect anywhere on the closed interval. Excuse me. Drink of water. Okay. And so you need to check to make sure that they don't intersect, and you don't have to do this. Sometimes they'll do that to you, and you know they can be kind of sneaky. They always want to test all the parts of the calculus as much as they can. So, all right, let's move on. The integral as an accumulator, and the big thing and this is for almost every application of the integral is summing up stuff, especially under kind of odd shaped curves. So the easiest example that I can talk about is a real simple differential equation, and this is a super duper simple example, but let's just say you earn $5 a day for 8 days. How much do you earn at the end of the week? Now, the pre-calculus, and when I say pre-calculus, I mean everything below calculus. The pre-calculus answer is simply you add up 5 days for each of the 8 days and you get $40. All right. But we can also think about it in terms of this differential equation. The change in earnings per change in day is 5. All right. So it's a differential equation. And so what that is essentially telling us is that earnings over the 8 days, time and earnings, that differential equation, this is the rate at which we get it. Since it's constant, we can actually calculate this area fairly simply. It's just a rectangle that's 8 by 5. We calculate that area. It's $40. All right, and we could do the integral of that if we wanted to. And again, it's fairly straightforward. You can just, again, we're integrating the differential equation and saying that E is going to be equal to, from 0 to 8, the 5 dt, which would be, again, just real quick, it's going to be 5t evaluated from 0 to 8, which would just be 5 times 8 minus 5 times 0. Again, we get $40. So again, the integral as an accumulator, this differential equation is going to give us a rate at which we can add up our earnings over the course of the 8 days. So again, that's a pretty simplistic one, but the basic concept still works. All right. Oops, I don't want to get that far. I mean, we don't have to have a constant function. If we have a function that we can define like this, then and your earnings change as time goes on, like for instance, if you get a lower rate for the first couple of days and a higher rate for the second couple of days, or it changes as you work, like a graduated scale, the more hours you get, the higher it goes. We have this odd shape. Well, now we can just find that area that way, again with the integral, as long as we know what this function is. All right, so let's move on to some examples. First example, number 20, sketch the region bounded by the graphs of the algebraic function, then find the area of the shaded region. And this shaded region is going to be the bounded region, so we need to talk about that. All right, so let's see here. Let's draw this thing. Let's see how we can do with this drawing. The line y equals x, that's pretty easy to draw in there. And let's make it kind of small. The line y equals x kind of looks like that. Again, if we call this x, we call this y. Negative x to the third, so a third degree polynomial that starts at the upper left, ends at the lower right, goes through 3. So we could draw in something like this, where this is 3. All right. And so let's see here, from x equals 1 to x equals negative 1. So if I put a 1 there and I put I put negative 1 and a positive 1 here, and I have like that. And I know that this point is not 1 because when I plug in 1, I get 1 out. So this would be 1, 1. When I plug in 1 here, I get 2. So I know that that intersection point is 1, 2. And so I know it's not that one, just in case you wanted to know. So the only bounded region between these values is this region right here. All right. And clearly, just in the context of the definitions, this is my f of x function, and this is my g of x function. This is going to be my lower bound, and this one's going to be my upper bound. So it's fairly easy to set it up. I'm just going to say the area is going to be the integral from 0, oops, sorry, not 0. I told you what the lower bound was, and then I screw it up. So negative 1 there is my lower bound. 1 is that one. Obviously, the function negative x to the third plus 3 is my f function, and then my g function is just going to be subtract x dx. And so if we simplify that, see if I can get this. So a equals, again, the integral from negative 1 to positive 1. We'll just have negative x to the third minus x, and then plus 3. And so that integral is going to be, let's see here, negative 1/4 x to the fourth minus 1/2 x squared plus 3x evaluated from negative 1 to 1. And again, I'm just doing the simple power rule on all three of those terms to make it real easy. And so I have to plug in, so I'll have, let's see here, negative 1/4 times 1 to the fourth minus 1/2 times 1 squared plus 3 times 1. And then it would be, I'm going to subtract from that negative 1/4 times negative 1 to the fourth power minus 1/2 times 1, negative 1 again to the second power plus 3 times negative 1. And if you calculate all of these things, it's kind of crazy. It comes out to be 6. Surprise, 6. And that's it. So you can calculate it out on your own, but it is 6. I checked. All right, so next example. Sketch the region bounded by the graph of the function and then find the area of the region. So again, this is, again, very, very similar. And so we want to, just to give us a kind of an idea, we want to draw the graph. And let's say here, I'm going to go from negative pi over 2. And so this, I'm going to make this positive pi over 2. And I know I don't have to go to that. I don't have to go to pi over 6. And so the difference between here is actually only, it's a third. Pi over 6 is a third. And so if I want to graph the sine function, I know some things about it. I know the sine function at negative pi over 2, the sine of negative pi over 2 is negative 1. Again, you got to go back to your unit circle. So, and then the sine of 0 is 0. And then the sine of pi over 2 is actually positive 1. And so I get a graph that looks like this, like that. Now, this cosine 2x, well, when you multiply the variable times 2, and this goes back to pre-calculus, really our first lesson in pre-calculus, this is a vertical stretch by a factor of 1/2. So we are shrinking the cosine function. So again, just plugging in some values here for the cosine function. If I plug in 2, or if I plug in negative pi over 2, negative pi over 2 times 2 is negative pi. The cosine of negative pi is negative 1, so I get that value again. Now again, it's squishing it by a half, and normally we count by quarter turns of pi over 2. So I'm going to put in negative pi over 4 because, again, we're squishing it by a factor of a half. And so negative pi over 4 times 2 is negative pi over 2. The cosine of negative pi over 2 is 0. And then at 0, the cosine of 0, because 0 times 2 is 0, the cosine of 0 is 1. And then at pi over 6, where we're going to end, because we're going to go from here to pi over 6, because they tell us that. And so at pi over 6 times 2 is pi over 3. The cosine of pi over 3 is actually 1/2. So pi over 6, and I didn't draw it very well. So we're just going to have to, you know what, I'm going to draw it so it looks right. I'm going to do it right, because you guys deserve it done right. And so we're going to go right through, still missed it. Go right through here, and then we'll stop like that. There we go. We'll get our half in. And so there's our half. Now here's the kooky thing is, again, the pi over 6, the sine of pi over 6 is also a half. So this graph looks like this, which is kind of groovy. And so over this interval, from negative pi over 2 to pi over 6, the closed region is going to be this shape right here. It's going to be right there. All right, so that's pretty cool. And so clearly, the greater function, even though it's listed as the g function, clearly the greater function, the function that's bigger for all the values in this interval, is the cosine of 2x. And so we're going to set up our area equation as the integral from negative pi over 2, the lower bound, to pi over 6, the upper bound, of cosine 2x plus sine x dx. Now, since it's a sum, one of the properties of integrals is that I can integrate both of them separately. So I'm going to go the integral from negative pi over 2 to pi over 6 cosine 2x dx, and then plus the integral from negative pi over 2 to pi over 6 sine x dx, and that should be a dot over there. Okay, I'm going to do them individually so that I can fix this, or I can do this integral. And since I have a composition of the 2x function and the cosine function, I have to do something with that 2x. The derivative of 2x is just 2. So I'm going to put a half out in front, and I'm going to put my integral negative pi over 2 to pi over 6, and then cosine of 2x, and then I have my 2 dx, because again, the derivative of 2x is just 2, so I need my 2 dx to get that. And then the second one's easy. It's just negative pi over 2 to pi over 6, and then it's just a sine x, so dx. So that's a simple integral. And honestly, you could probably do, this one won't come out as the exact answer. Never mind. Sorry. So doing this evaluation, I got a half, and then the derivative, or the integral of cosine, is sine 2x, and then the integral of negative sine, of sine, is negative cosine x, and I can't do it like that, sorry. Gotta evaluate this from negative pi over 2 to pi over 6, and then plus, again, and I needed, if I did it the way that I had it, I'd be distributing this half to both the sine 2x and then whatever the integral of this is. And the integral of this is the cosine of x from negative pi over 2 to pi over 6. Now, when you plug all of those values in, and again, you guys can do this, it's not that bad, it becomes a half sine of 2 times pi over 6, and then minus the sine of 2 times negative pi over 2, and then plus would be the cosine of pi over 6 minus the cosine of negative pi over 2. We're not, this lesson isn't about evaluating. You should know how to do that. And so when you get that all done, it comes out to be 3 square root of 3 all over 4. And again, I'm just doing that to make sure that we keep moving here, since I've gone pretty far already. All right, so estimate the area. Shoot, that should be AREA. Sorry that of the oil spill using the trapezoidal rule. So I'm going to set up a bunch of trapezoids, and you can see it's just a spill. And we're going to say that the width at the ends are 0. And so since every distance here is 4 miles, we can set up a bunch of trapezoids. And so remember, your area of a trapezoid is 1/2 the height times b1 plus b2. And in this particular instance, so each of these trapezoids is going to have the 1/2. And so essentially we can say that the area of this thing, or the estimate of the integral, will be, well, it's going to start with, it's going to be my 1/2, because each of them are going to have a half. And then my height is going to be 4 miles for each of those. And then again, just like you've done in the past, each of those trapezoids, this base counts, and then that base, that's the first trapezoid, but the second trapezoid has 11 and 13.5. So we'll be using each of these inside bases twice. So we'll have 0 plus 2 times 11 plus 2 times 13.5 plus 2 times 14.2 plus 2 times 14 plus 2 times 14.2 plus 2 times 15 plus 2 times 13.5, and then plus 0 because it has 0 width at this end again. And we'd only count those end sides once each. And so you can calculate that. All right, last one, then we're done. I have the return of the Star Wars fun fact of the day. I know you're excited. Okay, so find the area of the region between the line, or the function y equals absolute value x, and y equals 0.08x squared plus k, where k is, find k, or part A, find k where, and this should be y2 is tangent to the graph of y1. And then find the area of the shaded region. So the first thing I got to do, I got to find where this function is tangent to the square function. So I have something like this. So I got to find the place, and I didn't even draw it very well, but I got to find the place where that becomes tangent, and we can move it up and down on the graph. So we got to figure out the correct k to make that work. All right, so let's do that. So part A first. Part A is actually, or y sub 1 is actually a piecewise function, and it's the piecewise function negative x and positive x, and the negative x goes from negative infinity is less than, no, let's just do it right. Let's just do it as interval notation. Oops, sorry. Let's make it easier on ourselves here. And we'll just say where x is less than 0, and it's just positive x right here when x is greater than or equal to 0. All right, so this thing has a slope of -1, and this one has a slope of +1. So I got to figure out where this thing has, or what value, or excuse me, where this thing has a tangent line that is equal to plus or minus 1. All right, so the derivative of y2, pretty easy. Y prime is just going to be 0.16 x, then the derivative constant. And so I have to figure out where this slope is positive 1 or negative 1. All right, so if I set it equal to negative 1, or supposedly and 0.16 equal to 1, 0.16x, I'll get x equals negative 1 over 0.16, and 0.16x equal to, oops, no, I don't want that. Let's go back one more. There we go. I'll get x equal to 1 over 0.16, and both of these are equal to, let's see here, when I do that division, I'll get x equals, let's see, 6.25, I think. And this one would be negative, and this x equals negative or positive 6.25. And so when x equals negative 6.25 and positive 6.25, then the slope of this curve, regardless of what k is, will be equal to, we'll have the slope of 1, which is what I'm looking for. And so what I need to do is I need to plug my x equal to the 6.25 into the original equation and solve for k. So when I get negative, or let's go positive 6.25 squared times 0.8, or 0.08, sorry, I need that thing to be equal to 6.25. And why do I need it to be equal to 6.25? Because it's on this line, and this line is y equals x. So if this point is 6.25, then that point is also 6.25, and I need to find that k. So evaluating that, plus k, solving that for k, and again, you're just going to square this, multiply by 0.8, and subtract from both sides. You get a k equal to 3.125. So that's the k value, and my equation for y2 is 0.08, and do it right. y2 equals 0.08 x squared plus 3.125. All right, that's good. Now, this y equals 0.8 x squared plus 1.125 is obviously the higher value of the two. And so to part B, find the area of the shaded region, all we have to do is the integral now from negative 6.25 to positive 6.25 of y2 minus y1. And there's another problem. Remember, these two equations are different from each other, so I have a problem with that. So here's what I'm going to do, and this is kind of cool. I am going to say that this thing is equal to, since it's symmetrical, I'm just going to find this area here and double it. And that makes my life a lot easier. So I'm going to say that this is equal to 2 times the integral from 0 to 6.25 of that original, or this top equation, 0.08x squared plus 3.125 minus my x equation. My x equation is that line on the interval that I am actually calculating. So minus x dx for this whole thing. And again, we got a bunch of decimals in there. I'm not going to mess with that since I have a calculator and they didn't tell me I couldn't use a calculator. So I'm just going to grab my calculator, plug in the 2, plug in the 0 for the integral, plug this in. I don't even have to simplify it. And what that will spit out is 13.021. And that is the region of this area. And again, it's a lot bigger than it looks because, again, we're all the way out to 6.25, not too far away. Well, that's all I got, folks. So here is my Star Wars fun fact of the day, and just some size comparisons of the spherical death space platforms We have DS1 from Episode 4, New Hope. It was 160 kilometers wide. And then the second Death Star that they never actually finished was supposed to be 30% bigger. So approximately, it's bigger than, but it's approximately 200 kilometers across was going to be that one. And then finally for The Force Awakens, they built another Death Star-ish super weapon into the side of a planet, and that particular one was even bigger at a whopping 660 kilometers. Well, folks, that's all I got. I hope you have a good day, and I will see you in class. Bye.